Welcome to the deep dive. We're here to sift through the sources and pull out the key knowledge you need. Today, we're doing a fundamental deep dive into analytical chemistry. And look, this isn't just about, test tubes and beakers. It's really the rigorous science behind figuring out what things are made of and exactly how much is there. Our mission, basically, is to distill the core processes, the language they use, and some of the, well, surprisingly crucial insights from this field. Think of analytical chemistry as, like, the detective of science, always asking what's in this, and crucially, can I trust this evidence?
Exactly. And that detective work, it really kicks off with some pretty high-stakes problems. Analytical chemistry isn't just an academic exercise.
Yeah.
It's completely driven by what's needed in the real world. I mean, think about the challenge of developing, say, rapid and sensitive detectors for chemical warfare agents. That needs analysis that's instant and incredibly precise.
Absolutely. Or shifting gears maybe to public health. You might look at something that seems simple, like figuring out how much dust and soil kids ingest. But that analysis, it's
Yeah.
critical because that amount, it's a direct indicator, something measurable for exposure to pollutants, heavy metals, that kind of thing.
Right. So the goal is always clear, isn't it? Connect these sometimes abstract lab methods to real outcomes, whether that's public safety or maybe meeting regulations or even global security. And making that connection, well, it demands a really structured, disciplined way of tackling problems.
Okay, so let's try to unpack that mindset a bit. Before an analyst even, touches an instrument, there's this defined blueprint they follow. It's generally broken down into 5 steps, sort of brings order to the potential chaos. Step 1 is just identifying the problem and really defining it rigorously.
Then step 2, and this is critical, designing the experimental procedure. That means selecting the right methods, figuring out the precision you need, budgeting time, resources, all that planning. Then comes step 3. You actually do the experiment and carefully gather the data.
Right. Then 4, analyze that data you just collected. And finally, step 5, propose a solution back to the original problem.
But here's something really important for you to grasp. This isn't like a factory assembly line. It's not always sequential, not in a fixed way. There's this powerful feedback loop, you could call it, connecting steps 2, 3, and 4. So say you get to step 4, data analysis, and the results just aren't quite right. They're inconsistent or maybe not precise enough. Well, you're forced to cycle right back to step 2, redesign the experiment, maybe tweak the method.
Ah, I see. And that inefficiency, that looping back, that's probably where a lot of time can get sunk, right?
Definitely. But let's look at the start and end of this process too. Step 1, defining the problem, and step 5, proposing the solution, the analytical chemist. They rarely work completely alone. They have to collaborate with engineers, biologists, maybe policymakers, depending on the problem.
That makes sense. You need the context.
Precisely. You need context for the data you're generating. Like, if you were analyzing heavy metals in soil, you need an environmental scientist, maybe, to define what level is actually dangerous. That's step 1 context.
Okay.
And then in step 5, when you propose a solution, you need to make sure it's practical for, say, the city trying to clean up that site. Analytical chemistry kind of acts as the translator, between the hard data and how it gets used.
And like any translation, you absolutely need a precise language everyone agrees on. Which brings us to the, well, totally fundamental role of units. Just imagine being a lab tech and you get an instruction that just says, transfer 1.5 of your sample to a 100 volumetric flask and dilute to volume.
Oh, that's worse than useless. It's literally asking for a disaster. Is it 1.5 grams, milliliters,
Yeah.
moles even? And the flask, 100 milliliters, 100 liters. Without those fundamental SI units, basically the metric system, you just invite confusion. Massive potential for error.
Right. You avoid that whole mess by enforcing clear standards. You must write, and you should demand to read, the full instruction. Transfer 1.5 grams of your sample to a 100 milliliter volumetric flask and dilute to volume. Units turn vague instructions into, well, actionable, reproducible science.
And speaking of precise language, let's touch on a little technical nugget. Something that often distinguishes professional analysts from maybe general scientists. It's the difference between molarity and formality.
Ah, okay. They sound similar.
They do, and sometimes they are the same value, but the distinction tells you something about the chemical reality you're trying to measure.
Right. Most of us learn molarity, I think, defined as the concentration of a specific chemical species in solution. Like if you put acid in water, you'd measure the molarity of the H+ ions specifically.
Exactly. Formality, though. Formality is the total concentration of a substance you initially put into the solution. It doesn't care about the specific forms it might take once it's dissolved. So if you dissolve glucose, well, it just days as glucose molecules. In that case, it's molarity and formality. They're identical.
But if you dissolve something like sodium chloride, just table salt, in water.
Good example. It completely breaks apart, dissociates into sodium ions, Na plus, C, and chloride ions, CLA. The formality tells you the total amount of NaCl you originally added, like the recipe amount.
Whereas the molarity, if you're talking about the ions, tells you the concentration of those active separate bits floating around.
Precisely. And that's crucial sometimes maybe for regulatory testing. If you're analyzing a fertilizer, say, you might need the formality to check the manufacturer added the right total amount, but you'd need the molarity of the active components like phosphate ions to know what the plants can actually use.
Okay. So understanding that subtle difference, it shows you're really thinking about the trustworthiness of your data, which actually transitions us nicely into precision. How do analytical chemists make sure their numbers are actually reliable? It often comes down to rules that might seem a bit boring, honestly, but are scientifically sacred, like significant figures.
Yeah, sig figs. They're not just some arbitrary math rule you learn in school. They're a direct communication tool. Recording a measurement to the correct number of significant figures that tells everyone who reads it exactly how precisely the measurement was made. It reflects the limitations of the instrument you used.
Let's make that concrete. Use the classic example. Imagine you weigh something. You record its mass as, say, 1.762 grams, okay? Now, compare that to recording it as 1.7620 grams. What's the actual difference there? Just a zero at the end.
Oh, the difference is massive in terms of information. If you write 1.762 gram, you're implying you used a balance that could only measure reliably to the nearest milligram. That last digit, the 2, is uncertain. By not recording that trailing zero, you're effectively stating your measurement precision is only about plus or minus 1 milligram. 1 milligram.
Okay.
But what if you actually used a really precise, probably expensive analytical balance, one capable of weighing to the nearest tenth of a milligram?
Then you'd write.
Then you must write 1.7620 gram. That single trailing zero carries the full weight of that instrument's capability. It explicitly states the precision is much better, plus or minus zero point 0.1 milligrams, number 0.1 milligram. Leaving off that zero, it fundamentally misrepresents the quality of your work.
Wow. So much weight in a single zero.
Absolutely.
Yeah.
And this ties into another distinction people often blur, error versus uncertainty. They're definitely not synonyms in analytical chemistry.
Okay, let's clarify that. What's the analytical definition of error?
Error is the difference between a single measurement, or maybe the average of your measurements, and the true value. It's a measure of bias. We call this determinate error. It's caused by something specific you can often identify, like an uncalibrated instrument, or maybe a flawed technique. And crucially, it's the kind of error that can be and must be corrected for.
Right. So error is like a systematic skewness we can fix. What about uncertainty then?
Uncertainty is different. It's the inherent, unavoidable range of possible values for a measurement. Even after you've meticulously accounted for and corrected all known determinate errors, there's always some random fluctuation left over. Indeterminate error. You just can't eliminate it completely. That remaining range of possible results, the spread you see if you repeat the measurement many times, that is the uncertainty.
Got it. Error is fixable bias. Uncertainty is the unavoidable random spread. Maybe let's ground this with a foundational method. What about gravimetric analysis? Feels like it's been around forever, but it really embodies that fundamental rigor, doesn't it? Because it relies purely on mass.
Exactly. Gravimetry is analysis using mass as the signal. It's quite elegant, really, in its simplicity and reliability. A big advantage is it often doesn't need complex calibration standards, unlike, say, many spectroscopic methods. You're relying on fundamental stoichiometry and mass measurements.
So how does it work in practice? Give us an example.
Well, a common type is volatilization gravimetry. The idea is you use energy, usually heat, sometimes chemicals, to selectively remove a component that's volatile, meaning it turns into a gas easily. And you measure the change in mass. The classic classroom example is determining moisture content in food.
Right, you heat the food sample.
You heat it carefully, usually in an oven at a specific temperature, until all the water has evaporated. The mass difference before and after heating tells you exactly how much water was present. Simple as that.
So you're using a physical change, vaporization, to reveal chemical composition, and you trust it because mass is conserved.
Precisely. Or, another example, combustion analysis. You can burn an organic substance completely in oxygen. All the carbon in the sample gets converted to carbon dioxide, CO2. You trap that CO2 and weigh it. From the mass of the CO2 collected, you can calculate exactly how much carbon was in your original sample. It's direct, it's very reliable for major components, and yeah, it's foundational.
Okay, so gravimetry sounds great for things where you have a decent amount of sample and the component you want is a major part of it. But what happens when things get really messy, like a biological fluid, maybe blood plasma, or an environmental sample like river water? And the thing you care about, the analyte, is only there in tiny amounts. Trace levels, maybe ultra trace parts per million, parts per billion. You can't just weigh it out easily.
No, you definitely can't. That's when we need to bring in the separation masters.
Yeah.
Techniques designed to isolate or at least enrich those minute quantities from a really complex background, the matrix. We're talking primarily about chromatography and electrophoresis now.
Chromatography.
Okay.
The basic idea there, as I recall, is partitioning, right? Splitting things between phases.
That's the core concept. You have two phases, a mobile phase, which moves, and a stationary phase, which stays put. The components in your sample mixture get separated because they interact differently with these two phases. Some components might stick more strongly to the stationary phase, they move slowly. Others prefer the mobile phase and get swept along more quickly. That difference in speed causes the separation. And for analyzing liquids, especially things that don't easily vaporize, the real workhorse today is high-performance liquid chromatography, HPLC. It's absolutely essential in so many areas, analyzing complex drug formulations in pharma,
Right.
checking for nasty pollutants like polyaromatic hydrocarbons, PAHs in soil samples, validating ingredients in food or consumer products. HPLC is everywhere.
And one key thing for people to understand about HPLC is how you control the separation, isn't it? The
Yeah.
solvent seems critical.
Hugely critical. The choice of mobile phase, the solvent, and its properties relative to the stationary phase is how you tune the separation. In what's called normal phase HPLC, the stationary phase is polar, like silica. If you make your mobile phase, your solvent, more polar, the compounds tend to spend less time stuck to the polar stationary phase, so they move faster, shorter retention times.
Okay.
But actually, reverse phase HPLC is much more common these days, and there, as the name suggests, it's flipped. Stationary phase is nonpolar, often long hydrocarbon chains bonded to silica. So then if you make your mobile phase more polar, maybe by adding more water to an organic solvent like methanol, the nonpolar solids will stick more strongly to the nonpolar stationary phase and retain longer. By simply adjusting the ratio of solvents in the mobile phase, sometimes even during the run in what's called a gradient, the analyst can precisely control this separation to isolate the specific compounds they're interested in.
That flexibility is really powerful, but if we need to push the limits even further, get even better separation efficiency. You mentioned electrophoresis earlier, specifically capillary electrophoresis, or CE. I've heard this method can achieve absolutely massive theoretical plate counts, which is basically a measure of separation power, right? Like 100,000 to 200,000.
That's right. Those numbers are, well, they're staggering compared to traditional methods. To give you some perspective, a really good top-tier HPLC column might achieve maybe 10,000, perhaps 20,000 theoretical plates on a good day. CE routinely delivers an order of magnitude, sometimes more, improvement in that separating power. It's incredibly efficient.
How does CE get that kind of resolution? If it's not using a packed column like HPLC, what's the driving force? What's the trick?
The trick is a fascinating bit of physics called electroosmotic flow, EOF. This is a real nugget for understanding CE. The mechanism actually starts with the capillary tube itself. It's usually made of fused silica. The inner walls of this silica capillary, when they're in contact with the buffer solution, which is usually slightly alkaline, they naturally become negatively charged. Little silent groups form on the surface.
Okay, so the inside surface of the thin glass tube is negative.
Correct. Now, this negatively charged surface attracts positive ions, cations, from the buffer solution. They form a sort of layer right along the wall. It's called the electric double layer. Then we apply a very high voltage, a strong electric field, across the length of the capillary.
Right.
These positive ions in that layer near the wall, they're solvated, meaning they have water molecules clustered around them. And under the electric field, they start moving towards the negative electrode, the cathode.
Okay, the positive ions move towards the negative pole.
And because they're dragging their solvation shells, their water molecules, with them, and because of viscosity, they literally pull the entire bulk of the buffer solution along for the ride.
Wow, like a tiny, perfectly uniform river flowing through the capillary.
Exactly. It creates this incredibly uniform flat flow profile. We call it plug flow. It's not like the parabolic flow you get from pressure-driven systems like HPLC.
And that's the secret, that uniform flow.
That's the secret sauce. Because the whole solution moves at such a consistent rate across the capillary's diameter, the zones of separated analytes stay incredibly narrow. There's very little band broadening compared to other methods, and this leads to that ultra-high efficiency. Interestingly, unlike chromatography, the efficiency in CE is largely independent of the capillary's length. That uniform EOF is the key.
That's a completely different way of doing separation. Amazing. It allows for super precise analysis on tiny amounts of sample, I imagine.
Very small samples, yes, and often very fast separations too.
Incredible. So we've journeyed quite a bit here, from laying out that five-step problem-solving structure through the absolute necessity of precision, like knowing what that trailing zero on a weight actually means. And finally, getting into the weeds of separating really complex stuff using the sophisticated physics of capillary electrophoresis. It all just reinforces this core idea, doesn't it? Analytical chemistry lives and breathes rigor. Every tiny detail matters. That single zero carries real scientific weight.
It does. And this dedication to rigor, it brings us back to the bigger picture goal of analysis. Optimizing your resources, getting the most useful, most reliable information possible. We talked about error and uncertainty earlier.
Hmm.
But in any real-world analysis, the overall quality, the total variance you see in your final result,
Hmm.
is usually limited by one or two main things. Either it's the precision of your analytical method itself, done in the lab, or it's the variability introduced way back at the beginning during the sample collection process out in the field, or wherever the sample comes from.
Okay, so method variance versus sampling variance. This sets up a really critical question then for researchers, for you listening, anyone managing a lab or a scientific project. When does it actually become futile? When is it pointless to spend more time, more money trying to improve the precision of the analytical method itself?
Well, there's a pretty well-established guideline, actually. It comes down to comparing the standard deviations, the measures of spread, for those two sources of variation. The rule of thumb is this. You should probably stop spending resources trying to make your analytical method more precise when the standard deviation associated with the sampling process is more than about 3 times greater than the standard deviation of your analytical method.
Ah, okay. So if the uncertainty from just grabbing the sample is already 3 times bigger than the uncertainty in your lab measurement.
Exactly. At that point, improving the method further gives you diminishing returns, very rapidly diminishing returns.
That gives you a really clear benchmark for where to put your effort, your resources. If your team out collecting, say, water samples is doing it inconsistently, maybe grabbing samples from slightly different depths each time, then spending thousands on a brand new instrument back in the lab just to get an extra decimal place on the concentration, that's completely meaningless in the grand scheme of things.
It's scientifically useless at that point, frankly. When the method standard deviation is only 1/3 or less of the sampling standard deviation, those random errors from your fancy instrument, they only account for maybe 10% or less of the total uncertainty in the final number you report. The big problem isn't on the lab bench anymore. It's out in the field, or wherever the sample originates. You absolutely have to fix your sampling protocols first.
That is a fundamental insight. Really practical advice for optimizing work in, well, any scientific or industrial setting, I suppose. Thank you. This has been a great dive into the rigor, the precision, and the mindset of analytical chemistry today. And if you enjoyed understanding how chemists approach problems, think about how these foundational principles apply to other crucial analytical techniques, things like voltammetry or spectroscopy, or maybe flow injection analysis. They all build on this kind of structured thinking. We'll catch you on the next deep dive.